So I'm going to take this opportunity just to maybe expand a little bit on some of the other options for non-deletion individuals and non-mutation individuals as well. So I'll start off with a slide. There we go. So disclosures, I think the most important here is this talk was not written by ChatGPT. So I'm just going to put that out there to begin with. So I'm going to start with a slide from Barbara Baylis's talk. And so these are some of the options we're working with at a very simple biological level at the moment in terms of examining their functionality and utility for testing therapeutics. So the iPSCs, I'll go into that in a sec, and then a different type of model for iPSC and organoids, as Barbara Baylis mentioned, and then reporters as well. But I'll start with iPSCs. So this is a schematic, and it will go from the top left around. So if you have an individual, and if you take a biopsy, often it's a skin sample. In some cases, for example, it has been foreskin, just to give you an example of a specimen, but it could be blood as well. And then, as Barbara Baylis was talking about with the human stem cells or the hematopoietic stem cells, they could be taken from bone marrow. So in iPSCs, induced pluripotent stem cells, they need to be induced to be pluripotent. So in that case, the cells are then broken down, exposed to factors, and it seems to be a magic combination of these 4 factors, and we induce them to become pluripotent stem cells. So if we were to use the freshman example, if freshman's a first-year uni student, these pluripotent stem cells are more like sophomore kind of uni students. Their second year, they've kind of gone down that track of choosing an arts science degree or something or other. So they're kind of heading down a certain path, and they would not be expected to produce any type of organ. They would be a little bit more specialized. So you take these cells and you can grow them in culture, and you can grow them for long periods of time. And at some point you can signal them to differentiate to become more adult-like cells. You can then take those cells and test on them in a laboratory and high-throughput screening for therapeutic targets. I think the most important thing about Angelman syndrome, for example, is that if we just take the paternal allele, just looking at that, for example, so in the developed human, the paternal allele will be silenced by this antisense transcription factor. But when you generate induced pluripotent stem cells, you take away that silencing, and it goes back to having the potential in many ways to not be silenced. So that's a very important key factor there. And then once you differentiate that, you go back to being silenced on the paternal allele, but that allows you an opportunity to intervene. So for example, some of the studies that FAST are funding, for example, are where you take the iPSCs on the far right, they're unsilenced, and you can culture them in a dish, for example, and then transfect them with viruses to have them express, as we saw, the isoform UBE3A1, or you can have them express the lentivirus or adenovirus vectors. And so you can program them, and you can also CRISPR them as well, or have other interventions in that point, and you can then redirect them to become differentiated mature cells. And if they're silenced, you might have fixed the maternal allele, or you've prevented the silencing of the paternal allele when they become more differentiated. The other option, as mentioned with the hematopoietic stem cells, is if you could then transplant them back through a injection, such as a spinal tap injection, and that they wouldn't be taken up into the body again. Alternatively, you can then redirect those cells for further investigation and therapeutics. The great thing about this also is that they can be individualized. Okay, so if you have an individual, for example, you don't know the genotype, you can't automatically assume they're deletion or mutation. Maybe they're UPD, maybe they're an imprinting center defect. You can take those cells, grow them in culture theoretically, find out what they're doing, and you can find out which treatment would best suit that particular cell from that particular individual. So that's a very exciting field and can really individualize therapeutics. And even if, for example, those who don't have a genetic diagnosis could be investigated in this way, the whole process would be expected to take months before any therapeutics are known to be effective there. And as I said, those projects are being funded by FAST. So other projects include the mouse model genes and knockouts, and these are different mutations, or also importantly, there are other genes that get caught up in this mix in the region, and there are mouse models being made for knockouts of those genes to know what impact, if any, those genes have as well. Do we need to take them into consideration? And that's being done as well. And then there's the other biomarkers and outcome studies that are being funded by FAST. It's important to note that not all treatments being funded have the potential to treat non-deletion patients, but the whole field, regardless of Angelman syndrome or any other disease or developmental anomaly, would then is kind of in the same area in the sense that there are a lot of options being investigated as well. And FAST continues to pursue and seek those opportunities. I'm just going to leave it there and we'll move on to questions, I think. I might ask Dave and Barbara to come up. I will probably start. There's a lot of information this morning, so I'll probably start with maybe directing your attention to the brochure. And in that pillar 1 in the first page there, I just highlight, for example, that programs are already being done of the adeno-associated virus, and we've seen already where Jim Wilson's lab is using that. Importantly, the adeno-associated virus is also being used for Zolgensma at the moment to treat SMA, and that is given through an intravenous injection. It's a once-off injection into the vein. So then there's hematic stem cells, which are, in this case, infected with the lentivirus, and they're reinserted into the spinal cord to be taken up into the central nervous system. Enzyme replacement therapy, which has already shown demonstration with Batten disease, for example. So that's pillar 1. Pillar 2, we've seen ASOs presented by Dave Segal, and an example of this is nusinersen, also with SMA, and this is given through a spinal injection on a 3 to 4 monthly basis. And there's new and emerging treatments in terms of CRISPR and the others listed on that page. And downstream targets, there have been a number of trials in Angelman syndrome through the years, but they continue to be downstream targets, and we'll hear more about those later today. So I'll open the floor to questions. Thank you.